Have you ever been in a room so loud you couldn't hear yourself think? Or maybe an auditorium where every word echoes and gets all jumbled up? This happens because of sound waves bouncing around. Sound is energy, and when it hits a hard surface like a wall or a floor, it reflects back into the room. This makes spaces noisy and can make conversations, music, or even just concentrating really difficult. We care deeply about controlling this bouncing sound, a field we call acoustics. It's not just about making things quieter, it's about making them clearer and more pleasant for our ears. Consider this. Acoustic absorption is our secret weapon against unwanted noise. Instead of letting sound waves bounce around freely, we use special materials that can trap them. Think of it like throwing a super bouncy ball. If you throw it at a brick wall, it comes flying right back. But what if you throw it at a big, soft pillow? The ball just thuds and stops. The pillow absorbed the ball's energy. Acoustic absorbers do the same thing with sound energy. They are essential for creating environments where sound behaves the way we want it to, whether that's in a recording studio, a library, a concert hall, or even your own living room. The science behind this is all about energy transformation. Sound travels as a wave, causing air particles to vibrate back and forth. When this wave of vibrating particles hits an absorbing material, the material's structure forces those particles to move through tiny, complex pathways. As the air particles jostle and rub against the material's fibers, the sound energy is converted into a tiny, tiny amount of heat due to friction. It's an amazing and invisible energy swap. The sound wave goes in, but it doesn't come out with the same strength, because its energy has been changed into another form. So, mastering acoustic absorption allows us to engineer our sonic world. We can design classrooms where students can hear the teacher clearly, build offices where workers can focus without distraction, and create concert halls where the music sounds rich and beautiful from every single scene. By understanding how to stop sound from bouncing, we gain the power to build quieter, safer, and better sounding spaces for everyone. It's a fundamental part of physics that makes our modern world work and sound a whole lot better. It's science. Let's talk about some classic sound absorbers. You've probably seen them everywhere. Materials like foam sponges, fluffy mineral wool, fiberglass, and even simple cotton are fantastic at this job. These are all what we call porous absorbers. The word porous just means they are full of tiny holes, or pores. If you look at a piece of foam under a microscope, you'll see it's not solid at all. It's a complex, tangled web of interconnected tunnels and pockets. When a sound wave enters this maze, it gets trapped. It's like a labyrinth for sound. The magic happens inside these tiny passages. As the sound wave's energy pushes air particles through the material's structure, the particles rub against the fibers. This friction is key. Every little bit of rubbing action steals a little bit of the sound wave's energy, converting it into heat. It's not enough heat to feel, of course, but it's enough to weaken the sound wave significantly. By the time the wave makes its way through the material, if it makes it out at all, it's much quieter. This is why a thick cotton blanket can muffle a loud noise so effectively. Different porous materials work better for different types of sound. Generally, these materials are superstars at absorbing high-frequency sounds. Think of sounds like hisses, clicks, or the high-pitched whine of a machine. These sounds have shorter wavelengths and vibrate very quickly, which means they interact more with the fine fibers inside the material and lose their energy faster. For lower-frequency sounds, like the deep rumble of a truck, these materials need to be much thicker to be effective. The longer wavelength of low-frequency sound can sometimes pass right through a thin panel. So, the next time you see foam panels on the walls of a music room or thick insulation in a building, you'll know what's going on. They aren't just there for decoration. They are carefully chosen porous absorbers, working silently to turn unwanted sound energy into heat. It's a simple, elegant solution that relies on the fundamental principles of friction and energy conversion. From a kitchen sponge to industrial-grade fiberglass, the basic idea is the same. Give sound a complicated path to travel, and it will run out of energy along the way. Now, just having a flat piece of foam is good, but we can do better. Science has shown us that the shape and arrangement of these materials matter a lot. One of the coolest examples of this is the anechoic chamber, a room designed to be almost completely silent. The walls are covered in big foam wedges pointing into the room. Why wedges? It's all about giving the sound wave a better chance to be absorbed. When a sound wave hits the tip of a wedge, it doesn't have a flat surface to bounce off of. Instead, it's guided down into the deep valleys between the wedges. This wedge shape is brilliant because it helps with something called impedance matching. Impedance is basically a measure of how much a material resists the flow of energy. Air has a very low impedance, while a solid wall has a very high one. This big difference is why sound reflects so strongly off a wall. The wedges create a gradual transition from the low impedance of the air to the higher impedance of the absorbing material. The sound wave doesn't just hit a wall, it gently enters the foam, gets reflected between the wedges multiple times, and loses more energy with each bounce. We can also improve absorption by changing the material's internal structure. For instance, instead of using a uniform block of foam, we can layer materials with different densities. A layer of less dense foam on the surface can welcome the sound wave in, and a denser layer behind it can provide more friction and resistance to absorb the energy more effectively. This layering technique helps the absorber perform well across a wider range of sound frequencies, tackling both some mid-range and high-range sounds at the same time. It's like having a multi-tool for sound absorption. Another clever trick is to leave an air gap behind the porous panel. Placing an acoustic panel an inch or two away from the wall can dramatically boost its ability to absorb low-frequency sounds. The sound wave passes through the panel, bounces off the hard wall behind it, and then has to travel back through the panel again, getting a double dose of absorption. The air gap itself also acts as a kind of spring, helping to trap sound energy. By simply shaping, layering, and placing materials thoughtfully, we can engineer absorbers that are far more powerful than their basic components. While porous materials are great, they have their limits, especially with those pesky, long wavelength, low-frequency sounds, the deep rumbles and hums. To fight these, scientists have developed some truly amazing technologies. One of the most exciting is the microperforated panel, or MPP. Imagine a thin sheet of metal or plastic with thousands of sub-millimeter holes drilled into it. It doesn't look soft or spongy at all, but when you place it in front of an air gap, it becomes an incredible sound absorber. It works on the principle of resonance. Here's how. The air trapped in each tiny hole acts like a small mass, and the larger pocket of air behind the panel acts like a spring. Together, they form a resonator, like a tiny tuning fork. When a sound wave with the right frequency hits the panel, it makes the air in the holes vibrate intensely. This intense vibration creates a lot of friction as the air rubs against the sides of the tiny holes, converting the sound energy into heat very efficiently. MPPs are fantastic because they are durable, clean, and can even be transparent, but they absorb sound like a thick foam panel. Taking this a step further, we enter the world of acoustic metamaterials. These are engineered materials with special internal structures that give them properties not found in nature. For low-frequency sound, one simple type is a membrane absorber. This is basically a flexible sheet, like a piece of rubber or vinyl, stretched over a sealed box of air. When a low-frequency sound wave hits the membrane, it causes the entire sheet to vibrate. The trapped air inside acts as a spring, pushing back. This vibration process flexes the material and dissipates the sound energy as heat, effectively trapping that deep hum. The ultimate goal for perfect sound control is to combine these different techniques. A single material is rarely the answer for all types of noise. The most effective solutions often use a hybrid approach. Imagine a wall system that combines a dense membrane absorber to cancel out low-frequency traffic rumble, a microperforated panel to handle mid-range hums, and a top layer of porous foam to soak up high-frequency chatter. By combining traditional porous absorbers with advanced resonant panels and metamaterials, we can create solutions that provide broad-spectrum sound absorption, making any space perfectly quiet and clear. The future of sound control is not just one thing, it's everything, working together.